Okay, good morning, everyone. So today we're going to continue talking about scattering problems in one dimension. And so our first example is going to be 1D scattering. Later we'll graduate to 3 dimensions, but it's 1D scattering from a potential rectangular barrier. Okay, and so this barrier is going to have width, which is a length scale of A, and height, which is an energy of V. And we might as well choose the origin to be right at the center of where our barrier is. So if we just draw a picture of it, here is potential as a function of position. And here's going to be minus A over 2. And on the right will be A over 2. And so the shape of this barrier looks like this. It's 0. Then it bumps up immediately to some finite value V, comes back down like so. Okay, and so this height is we're also going to call V. And then we're going to divide this into regions the way we did last time. So on the far left is region 1, on the far right is region 2, and this time we have one intermediate region, region 3 here. Okay, and just to write down a formula for the potential, this is equal to 0 if the absolute value of x is less than A over 2, and it's equal to V otherwise. Okay, now when we're doing scattering problems, we're going to look for a stationary state with some energy. That energy E is supposed to be the energy at which we're sending in particles. And then our goal is to find the reflection and transmission coefficients. Okay, and as a reminder, those are probabilities. And so they satisfy the usual things that probabilities have to satisfy. Namely, they have to be between 0 and 1. And because they reflect different outcomes, that means the sum of them has to equal 1. And so we're trying to compute something that we could, in principle, measure if this were a real experiment, which is the probability that a particle that we send in gets reflected back at us or transmitted through the barrier. Those are the two possible outcomes. Okay, so now since we have the energy E, we can write down the form of the wave function in each of our regions. In region 1, there's going to be a wave that we send in, and we put the coefficient of that equal to 1. And then there's some wave that would be the reflected wave coming back at us. And we put a coefficient B there in front of that. We've already used up the freedom to decide what the coefficient of the incoming wave is. So B has to be a free variable. Okay, and then in region 3, it's some other coefficient times a different wave. So I'm going to call that K prime. And there can be a wave moving in either direction. So there's e to the I k prime x and e to the minus I k prime x. And then in region 2, on the far right, we're assuming that there's no wave coming in towards the barrier over there. There's nobody sending in a wave over there, and therefore it's all moving to the right. So there it's c e to the I kx. And the values of k and k prime are given by, if we're in regions 1 and 2, then E equals h bar squared k squared over 2m from the Schrodinger equation. And it also is equal to, in the intermediate region, h bar squared k prime squared over 2m has to equal E minus V. Okay, so those are what you get just by plugging into the Schrodinger equation. So we know what k and k prime are. When we solve for B, the reflection coefficient will be that thing squared, since we chose the thing we had called last time A to be 1. Okay, it's just the ratio of those two things squared. So if A is 1, then the reflection coefficient is B squared. And the transmission coefficient is just going to be C squared, the way we've set this up. Okay, and so we have, at this point, 4 unknowns, namely B, C, D, and F. And we want to solve for those, but really what we want to solve for is just B and C. We don't really care that much what D and F are, although in principle we would be solving for them along the way anyway. Okay, so now the strategy is, as boundary conditions, we look at our 2 points between the regions, and we're going to apply continuity of the wave function and its first derivative at those points. Okay, so there's, first of all, continuity at x equals minus a over 2. And so we just plug in our 2 wave functions that meet there, this one and that one. And so for the wave function, our equations look like this: e to the minus I ka over 2 plus b e to the I ka over 2 has to equal d e to the minus I k prime a over 2. Remember, we know k prime. That's not an unknown. And f e to the I k prime a over 2. And then, because the potential is finite at that point, we get to also match the first derivative of the wave function. And all that does is, here you pull down a factor of ik, you pull down a factor of minus ik when you take the derivative of that. You pull down a factor of ik prime, and you pull down a factor of minus ik prime there. So we just have to write those factors in. Ik e to the minus I k a over 2 minus b e to the plus I k a over 2. Okay, and then on the right side, we're putting k primes. From the derivatives. Okay, so we have 2 equations, but we have 4 unknowns. And so we're also going to be imposing continuity at x equals a over 2. So there it's c e to the I k a over 2 has to match with d e to the I k prime a over 2 plus f e to the minus I k prime a over 2. And then that's the wave function continuity. And then there's the first derivative that we have to impose. And there we're just going to have an ik from taking the first derivative in region 2 and an ik prime in region 3. Okay, but there's always a minus sign if it's a left moving wave when you take the derivative. Okay, so there we have 4 equations and 4 unknowns, and we need to solve those equations. So one thing that happens a lot and happens in scattering problems and happens in this case too, is that if you just say, oh, I've got 4 equations and 4 unknowns, let me just go ahead and solve for them, you're likely to make yourself suffer more than you need to because the algebra will get really hard. So it turns out, and I wish I could give you sort of rules for how to minimize the effort, but I don't know rules that always work. But it does turn out that it's, if you adopt a better strategy, you will minimize your pain and suffering. So in this particular case, it just so happens that the most efficient way to do the solution algebraically is to solve the last 2 equations first. And those equations involve 3 variables, but you want to solve for D and F. Okay, so you're solving for D and F in terms of C, and then you can plug D and F here, 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 and here in the first 2 equations. And then what you want to do is solve for B. Okay, so then solve for first 2 equations for B. So when you do that, you're solving for B in terms of C, and the answer turns out to be not too bad. It's B is equal to C times A k prime squared minus k squared over 2k k prime times sine k prime A. So the sine k prime A comes about here because of your exponentials. And so you're using the rules for writing exponentials of imaginary quantities in terms of sines and cosines. And so it just sort of works out that B in terms of C is very simple, or relatively simple. So now you can either solve the other one of those 2 equations from the first 2 equations, but it's actually more efficient to use the fact that we know that our reflection coefficient and our transmission coefficient add up to 1, and one of them is just B squared, and the other one is just C squared. Okay, so now we can write here that we also know the magnitude of B squared plus the magnitude of C squared is 1. And so rather than trying to solve for C or B individually, since B squared and C squared are what we actually want, we just solve for them. And so when you do that, you get C squared is equal to 1 plus this coefficient, k prime squared minus k squared over 2k k prime, sine squared k prime A. So I take all of that and I take the reciprocal, and that's C squared. So notice the idea is I didn't ever bother solving for B, C, D, and F. I only solved for the magnitude of C squared. And then if I want the magnitude of B squared, it's just 1 minus that. Okay, and so this is the transmission coefficient. And then if you want the reflection coefficient, it's just 1 minus that. So a lot of times what you want to do is write your answer in terms of the energy of the particles that you're sending in. So we can do that pretty easily. We can plug in that if you solve for k prime, it's equal to k times square root of 1 minus the potential barrier over the energy. Okay, that came from back here. Those 2 equations allow you to solve for k prime. Okay, and so we can write the transmission coefficient, that was our actual goal, as 1 plus v squared. Notice all the k's and k primes are just canceling. And we write everything in terms of the energy, the barrier height, and the width of the barrier. So it kind of makes sense that the answer, those are the only things the answer should depend on. And that is your transmission coefficient. Okay, so now we can look at some special cases just to see what happens. So a good special case to always look at is what happens in the extreme case of v equals 0. If v equals 0, there's no barrier at all. And so in that case, if I plug into that t, I indeed get the whole wave is transmitted. There's no barrier to do anything to it. And so the only thing it can do is get transmitted, and the reflection coefficient will be 0. So that's one way of getting a perfect transmission, but it's not the only way to get a perfect transmission. We also have transmission coefficient of 1 if we just manage to make this sine function be 0, because if that's 0, then it's just 1 plus 0 reciprocal. And so sine functions can often be 0. What it takes is we need, well, one way of writing it is that a times k prime equals n times pi. So here I'm going back up to this version of it. Okay, and so if that's true, then that means k prime is n times pi over a for some integer n. That will make the sine function vanish. And so the barrier will be transparent, meaning t equals 1. If the width of the barrier, which is, we called it a, if that equals n times half a wavelength
I'm
of
sorry,
the
Professor.
particle in the barrier. Sorry, go ahead.
Sorry to interrupt you. So these are both t equals 1? Because you said also have t equals 1?
Right, so we're looking at conditions that will give us t equals 1, which means the barrier is transparent. So one way is the potential is 0, but even if the potential isn't 0, we can do it if a k prime is n pi. Okay?
Where does the ak prime? Okay, that goes up to the previous, the c squared, correct?
That comes, yeah. So this was just a rewriting of that. And so either way, if a k prime is an integer multiple of pi, then this will vanish.
Thank you.
Okay. Also, even if neither of those two things are true, if the energy is much, much larger than the barrier, that will also give t approximately 1. And the way of thinking about that is if you have very high energy particles coming in, they don't care that there's some puny little barrier there that's barely measurable compared to their energy. And so the sine squared, this time we'll use the second version of the sine function. Okay, and so all we're going to do here is say that that's approximately equal to 2a squared m e minus v over h bar squared. So all I'm using there is that the sine of a very small number is approximately the same very small number. Okay, and so in that limit where the energy is very large, the transmission coefficient is approximately 1 plus a little bit. And you have to take the reciprocal, of course, because t has to be less than 1, can't be greater than 1. Okay, so now all of that assumed that our energy was greater than the barrier height. So one place where we assumed that is when, for example, I wrote this right here, or even when I wrote this right here. If my energy was less than the barrier height, then I'm taking the square root of a negative number, which is imaginary. And so I should think about that situation separately. Okay, so let me write here all of that assumed energy greater than barrier height. And now we can ask, what if it's not? What if the energy is less than the barrier height? So actually all the same algebra goes through, okay, except in the bump region or in the barrier region, instead of writing e to the I kx, I should write a linear combination of exponentials.
Sorry, Professor.
Yes?
I'm sorry to interrupt you again. I'm a little bit slow. What happened up there? The sine squared equals 2a squared?
Right. So we're assuming we're oh, sorry, I was doing something else there. Good question. So there I was actually looking at the case, I forgot to write this down. If the energy is approximately equal to V. Okay, so if the energy is approximately equal to V, then this is a very small number. So we're taking the sine of a very small number. Sine of a very small number is equal to the same very small number. And so I just take that thing squared.
Thank you.
Sure. So I should have said here, this is for energy approximately equal to V. Good. Okay. All right. So going back to the case where the energy is less than the barrier height, okay, we should write this down instead. And where, when you solve the Schrodinger equation, kappa is equal to square root of 2m e minus v over h bar. Okay, and so basically all the algebra is going to be the same with one change. Okay, and that change is, instead of writing k prime everywhere, I'm going to write I times kappa, because that's what it is. And so if you follow it through, that means wherever I wrote sine squared, I should have written, or I could write I hyperbolic sine squared. Okay, and so in that case, the transmission coefficient is 1 plus v squared over 4e v minus e, hyperbolic sine instead of ordinary sine. And then the argument of it will be a real number, because e is less than v, and so square root of v minus e is a real number. Okay, and notice again, this is less than 1, as it has to be. And it has to be a real number. It's always good to check that these things are real numbers. Okay, and so for e much, much less than v, basically we have a transmission coefficient which is 1 plus the reciprocal of a very small number, and then the reciprocal of all of that, which is a very small number. Okay, and so that will go to 0 in the limit where the energy becomes very small. All right, so now we can put back all those subcases into and draw a picture of what the transmission coefficient will look like as a function of E over V. So this is transmission coefficient. Of course, it has to be between 0 and 1. Okay, and what we just worked out is that for very small e, it's very small. Let me put 1 here. Okay, and so it stays less than 1. But then when we increase it, eventually it will actually get up to 1. That's the case where the we just happen to have half a wavelength fit within the barrier. And then there's several energies where it can do that. Let me draw a dashed line for 1 here.
Professor?
Yes.
I'm sorry, I fell behind again. That h squared, is that hyperbolic or is that the h Planck? The sine square, I sine square, h.
This, sorry, this,
Both
this.
like that one and the bottom. Yeah, I fell behind a little bit. What
Right,
happened?
those are hyperbolic signs.
Oh, okay. Okay, thank you.
Okay. Right. So, and then when the energy is very large, we found it must approach 1. That's saying when the energy is very large, it doesn't care that there's a puny little barrier there. But also there's transparency at an infinite number of different places. Okay, and that is going back up to here. That was, we had this condition that would work for any integer n, and so there's an infinite number of different integers n, and those are these points right here, where the barrier, you're actually transparent to the barrier. Okay, and then this region here is called the tunneling region. Because there you're not allowed to send a particle through classically, and yet quantum mechanically it does go through. So it's not allowed classically to transmit a particle because you don't have enough energy to get through the barrier. But what we find is that quantum mechanically, so just to draw a picture, here's our barrier. Here's this is V. Here's the energy level of the state that we're sending through. And so what's happening is that the wave function is an e to the I kx in here. I'll draw that cartoonishly as a wiggle. And then here it exponentially decays, and then it wiggles on the other side. I guess I should have really, so actually it's e to the I kx, so it's not really sines and cosines. But if you look at, say, the real part of the wave function, it does something like that. Okay. So that's a quantum mechanical feature that you don't see classically, is that you can make it through barriers that classically you would not be allowed to do. Okay, other questions on that? All right, so let's do the cousin of this problem, which is 1D scattering instead of from a barrier,
Professor.
from a potential well. Yeah, go ahead.
Could you just scroll up a little bit? Thank you.
Okay. Okay, so what does this 1D scattering from a potential well mean? It just means that my pen isn't working. Again, I don't know what's going on. Okay, so it means the potential is, instead of going to be positive, it's going to be negative. So it's still 0 if you're outside of the region A/2, but now it's going to be minus its absolute value if x is less than A/2 in magnitude. Okay, and so drawing that There's minus A over 2. There's A over 2. And the potential well looks like this. Okay, and the good thing is that we can just steal all the algebra that we already did to get the answer. It doesn't actually require anything new. So same algebra as before, meaning for the barrier. It's just that we have to replace V by minus its absolute value. And so we can just go ahead and write down without further ado what the transmission coefficient is. 1 plus V squared over 4E, E plus V sine squared. Okay, instead of E minus V, it's E plus V in absolute value. And then the reciprocal of the whole thing. Okay, so that's the formula we're going to use, and now let's figure out what some of the things are that this means. So one interesting fact is that for energy goes to 0, the transmission coefficient is going to go to 0. Okay, and the reason for that is that when the energy goes to 0, I'm trying to divide by 0 here, which means I'm getting a very large number for all of this stuff, but then I'm taking the reciprocal. And so the transmission coefficient is going to 0. And so the interesting thing about that is it's very non-classical. Even though we're not doing any tunneling, we're sending in an energy that's positive but non-zero. We're sending in some energy that's at this level. And so you would think classically the particle should just go just fine to the right. But quantum mechanically, it does not do that. And so sort of what's happening is it's getting all reflected back by this end of the barrier. That's tending to send you back again. In any case, the algebra doesn't lie. And the algebra says for E goes to 0, there's no transmission. On the other hand, you can have transmission going to 1, just as before. Okay, first of all, if the energy is very large, once again, if the energy is very large, it doesn't care whether there's a well there or a barrier or what, doesn't matter. It's just going to transmit. Okay, or it can get transmitted again if the argument of this sine function here happens to be giving you a 0 value for the sine function. So that would be A over h bar, square root of 2m E plus V, is some integer multiple of pi. Okay, or another way of saying it is that it will happen if the energy of the particles you're sending in are minus V plus, I'm just going to solve that previous equation, and I'm going to get h bar squared n squared pi squared over 2ma squared. Okay, so I can write that as E sub n minus V, where E sub n is that thing. And so if you stare at that, you realize these are the binding energies for bound states.
How did you calculate that E?
How did I calculate the E sub n? Or
Yeah. E, okay, so you got E
I'm
is,
solving this equation for E.
oh, okay. Okay.
All right, so these are the binding energies of bound states, but not the bound states of the potential that we're actually scattering from. They're bound states for a different potential, namely the potential of a box of width 2a, or sorry, width a. Okay, so this is, by box, I mean something with infinitely high potential wells. And so this is an infinite potential, not the potential we're actually scattering from. So it's not the same as the potential we're scattering from. But somehow this scattering problem knows that if you happen to send in a particle with energy corresponding to an infinitely tall potential with the same width, then the transmission coefficient will go to 1, and the thing will be transparent. Okay, so once again, we can draw a picture of the transmission coefficient as a function of the energy normalized to the potential well depth. And so here's 1 and 2, etc. And so once again, for very small energies, the transmission coefficient is 0. But then what can happen is, here's t equals 1. What can happen is there are these resonance energies. And if you just happen to be near a resonance energy, then the transmission coefficient again will go to 1. Okay, and the height of these peaks is larger if the potential is very deep. Okay, so just to draw some things here, this is very small t, even though it's classically allowed. So this is very quantum behavior. Okay, and each one of these points where you have resonances is a transparency point. Okay, and so there's lots of different versions of this depending on how big you assume the potential is compared to how wide it is. But this is actually something that's seen in the real world. This is called the Ramsauer-Townsend effect. That might be how you spell Townsend and Ramsauer, I'm not sure. Okay, and so the statement of this effect is that an attractive potential becomes almost transparent and the reason I say almost is because you don't really, in nature, you don't really run into perfect rectangular wells or anything like that. That's why it's only approximate. So it's almost transparent to scattering for certain discrete energy values. Okay, and what discrete energy values are they? They're determined by the geometry. Okay, and so in the real world, the way you see this is, or the outstanding case where this arises is when you scatter electrons from noble gas atoms. And specifically from argon, krypton, and xenon. And so if you look at the potential that you get from those kind of atoms, because they're noble gases, they tend to have a complete shell. And so if I graph as a function of distance, what the potential looks like, it looks something like this as a function of distance. So when you get very far away from the nucleus, then you have all the other electrons that are screening out the nucleus and you get zero potential. So this is screening by other electrons. But the wave functions for those electron states are very small near the origin. And so when you're close to the origin, you don't see them. And that's why the potential becomes very attractive. inside the closed electron shells. Okay, and so what's observed when you do this scattering is that they're close to transparent for a certain electron energy, which turns out to be a little less than an electron volt. So energy is about 0.7 electron volts. Of course, to get that number out, you have to kind of put in the details of all the potential, but qualitatively, it's the same effect that we've just seen. Okay, any questions on that? All right, I think we'll now graduate as promised to three-dimensional scattering. And by the way, after doing a lot of work, we'll be able to come back to the Ramsauer-Townsend effect in real three-dimensional potentials and see how it works. Okay, so here's the typical problem in three-dimensional scattering. We're going to send in free particles with some fixed energy and therefore with fixed momentum. Okay, so now it's a vector rather than just a number. P equals h bar k towards a region with potential. And we're assuming the potential is localized so that it doesn't extend over very large distances. Okay, and so the cartoon version of this is here's our wave coming in. Here's some potential region. I'm just drawing it as a shaded blob. And we're going to choose our wave vector because we can. We're just going to choose it to be in the z direction. That's just a choice of coordinate. This blob is our region where v of r is non-zero. Okay, and when I draw these straight lines, what I'm really drawing is the wave function constant lines of phase. So for example, I could choose to draw a line wherever the phase happens to be 0. Okay, and so let's describe that wave function. We know how to draw a plane wave or to write down a plane wave. Okay, there's some normalization factor which we're going to take to be 1 over 2 pi to the 3/2, which is really pretty arbitrary. It's kind of like choosing the freedom to choose A in the one-dimensional problem, times e to the I k dot r. Okay, and so this is the wave function of our state k. And this is the solution if there were no potential. In a little bit, we're going to have to write down the solution with a potential. But before doing that, I just want to say one thing about the normalization here. I didn't choose that normalization completely at random. The normalization is supposed to be fixed so that if I do the inner product of two different waves like that, the way it's normalized, if you go back to how we defined the delta function, it had the 1 over 2 pi cubed in it. And so this is nothing other than a three-dimensional delta function of k minus k prime. Okay, so that will be important later when we want to do calculations with these things. We have to know how to normalize the overlap between two different states like that. Okay, so now let's say we take into account the potential. Let's just first draw a picture of what it's going to look like. Okay, so here's our potential region again. This is some blob. We're sending in our plane wave. And out is going to come some spherical waves. I should draw a complete spherical. These are, again, lines of constant phase. And these describe an outward flux of particles. And so not today, but next time we will be figuring out exactly how we describe the outward flux of particles with these waves going out. So rather than do that, let me just give an idea of where we're going. I'm going to write down a formula without justifying it. And then we will work hard to prove that the formula I'm writing down is actually true. But just to give an idea where we're going, let's write the form of the answer in advance. Okay, and so here's going to be our scattering wave function. So first I'm going to write my 1/2 pi to the 3/2 times our e to the I kz. So that's describing our incoming beam of waves. And then our outgoing beam of waves is going to look something like this. E to the I kr. So instead of e to the I kz, it's e to the I kr because the waves are moving in the radial direction. And so constant phase is at constant radius. And then I have to divide by r, it turns out, to get this to make sense. And then there's some factor that depends on k, but it also depends on the angle, because the waves that are going out don't have to be the same. For example, if I'm here rather than here, rather than here. So these waves can depend on theta and phi. Okay, so that's the form of the wave function, and that's supposed to be true for large r, very far from the target. It turns out this won't be the correct formula if you're close to the target, but in some sense, we set up our detectors very, very far away, and then this is the only part that we'll eventually end up caring about. Okay, so just to label some of these things, this is our incoming plane wave. Okay, the wave vector for the plane wave is just in the z-hat direction. This is an outgoing spherical wave. Again, I haven't justified that it actually looks like this, but I promise you we will prove that. And the key thing about here is that because if we look very far away from the target, because energy has to be conserved, this k and that k are the same k. So going from the incoming wave to the outgoing wave, the energy is staying the same. Once I'm very far away from the target, there's no potential out there to change the energy. And so they have to be the same, but the direction is changing. All right, so let me now write down the tasks that we will solve in the next few lectures. Task 0 is really to, before we do anything else, figure out what we're trying to do. So figure out what we want to compute and measure. And the analog of the reflection and transmission coefficients, R and T, is instead going to be something called differential cross-section. Instead of just being two numbers, it's going to be in 3 dimensions. It's going to be an infinite number of different numbers, but organized as a function. Okay, our next task, I guess I started at task 0, so this is actually task 1, is to prove the above equation and along the way, find an equation for our f sub k function. Okay, those two things will sort of go hand in hand. And then our next task is to find the solutions. Okay, and there we'll do it sort of two ways. We'll do it in an exact formal way. Formal here is kind of a synonym for useless, right? Because if it's formal, it just means that you can't actually do much with it practically. And so to do something useful, you usually have to make approximations. So we'll learn how to do those two things. And then we'll sort of go back to task 0 again, which is to interpret the results in terms of observable quantities, namely the cross-section, the differential cross-section. Okay, so that is our goal going forward. And so that's it for today. Any questions on today's lecture?
Professor, I'm just curious, how far on the notes will you get into, and how many more sessions do we have?
I have no clue how far we're going to get. My plan is just sort of to go until we're done, until we run out of time. So I'm not really sure. It kind of depends.
So is that to carry on into the 686 course that they're talking about you teaching next semester?
No, 686 is a quite different thing, which will not really carry on from this.
Well, what are the prerequisites for that one?
So prerequisites for 686 would be this class, and it's probably necessary to have had 670, 671, and have some familiarity with, at least a little tiny bit of familiarity, I'd say, with special relativity.
Okay, so if we haven't had 671 yet, we wouldn't have the prerequisites for that course, correct?
Not technically. I mean, I think it would be ideal to have had 671, but you know, it might work out. It might be okay anyway. I think it would be much more difficult if you haven't had 670 and 671, but it's not necessarily. I think the official prerequisite might include those. I'm not sure. All right. Any other questions? If not, we will see you on Wednesday.
Thank you.